Energy availability is the single largest constraint currently facing data centers and heavy industrial operations. In our last discussion, we explored why utility delays and grid congestion are stalling multi-billion-dollar projects. But today, we need to answer the logical next question. If the grid isn't coming to you, what does it actually look like to bring the power to the site? Specifically, how do you move from a fuel source all the way to that first megawatt of reliable energy? It's a journey that involves far more than just dropping a generator in a field.
The common misconception is that distributed energy is just about the equipment. People see a reciprocating engine or a turbine and think the problem is solved. In reality, a generator is just one link in a very long, complex chain. To get to that first megawatt, you're essentially building a mini utility on site. You have to handle fuel procurement, cryogenic logistics, storage, regasification, and 24/7 field operations. If any one of those pieces fails, the generator is just an expensive piece of steel sitting in the dirt. It's why UNRG approaches this through what they call the Energy Fulfillment Platform. It's about moving from fragmented vendors to a single integrated operating system.
So let's walk through that chain. It starts before any equipment even moves. When an operator realizes they have a power gap, how do they determine what they actually need? It seems like simple math, total up the servers or the industrial load, but I suspect it's more nuanced than that.
It's extremely nuanced because you aren't just looking at the peak load. You have to understand the operating schedule, the location's climate, and the required uptime. For a data center, 99.99% reliability is the baseline. We also look at growth plans. If a facility needs 10 megawatts today, but plans to scale to 50 in 3 years, the infrastructure needs to be modular. We analyze existing utility availability too. Sometimes it's a bridge solution until the grid arrives. Other times, the site will stay behind the meter indefinitely. This initial assessment defines the entire system design.
Once you have the load profile, the next hurdle is the fuel. In this model, we're talking about natural gas and LNG. Why is securing the supply the first real logistical priority? Most people probably assume you just call a gas company once the generators are hooked up.
That's a recipe for an outage. In distributed energy, fuel security is power security. You need a dependable LNG or natural gas supply before a single truck leaves. UNRG manages this through their open market fuels model, where they source from established domestic networks. For instance, their facility in Seminole, Texas, produces 100,000 gallons of LNG per day. Having that captive production or secured plant gate access is what allows for the never-empty supply programs. You cannot risk a site going dark because a third-party supplier had a hiccup or because you didn't account for market volatility.
And the logistics of moving that fuel is where it gets physically challenging. If a data center or a remote mine isn't on a pipeline, you're moving LNG at minus 260 degrees Fahrenheit across highways. That isn't standard trucking.
It requires specialized cryogenic transport. This is what UNRG refers to as molecules in motion. You're using insulated trailers designed to keep the gas in its liquid state. In its liquid form, natural gas is 600 times smaller in volume than it is as a gas, which is the only way to move the massive amounts of energy these sites require. But it's not just the driving, it's the scheduling. You need a virtual pipeline where trucks arrive in a perfectly timed sequence to keep the on-site storage tanks at the right levels. If the trucks are late, the power stops.
When the LNG actually arrives at the site, it can't go straight into the engine. It's a liquid at cryogenic temperatures. Walk me through what happens in that middle stage, the storage and the regasification.
Exactly. The engine needs gas, not a liquid at minus 260. So we have on-site cryogenic storage tanks that act as a buffer. From those tanks, the LNG goes through a regasification unit, basically a high-tech heat exchanger. It uses ambient air or a secondary heat source to warm the liquid until it expands back into a gaseous state. This has to be controlled very precisely to maintain the correct pressure and flow rate to the generators. It's a modular setup, so if the power demand grows, you add more storage and more regas capacity. It's all about ensuring the fuel is always ready for the moment the engines demand it.
So now we finally get to the power generation equipment. We've assessed the load, secured the fuel, handled the logistics, and regasified it. How do you actually select the right generation units? Is it just a matter of picking the biggest engine available?
Hardly. Configuration is everything. For industrial and data center loads, we often use megawatt-scale reciprocating engines because they handle load steps very well. They can ramp up and down as the customer's demand changes. We also have to build in redundancy. If a site needs 10 megawatts, you might deploy 12 or 14 megawatts of capacity. That way, if one unit needs maintenance, the site stays at full power. This is the core of the Be the Grid model. It's a turnkey system where the fuel and the power are designed to work as one integrated unit. If the customer already has fuel, say a gas pipeline, they might just use the watts-only model, which focuses solely on the generation and operation.
The deployment itself sounds like a massive field operation. You have multi-ton tanks, Regas units, and generators arriving at a site that might be a remote oil field or a new construction zone for a data center. What does that field execution look like on the ground?
It's a high-stakes coordination of civil work, electrical integration, and mechanical assembly. You have to prep the site. Sometimes that's pads for the equipment or trenching for the cables. Then the mobilization starts. UNRG uses modular, containerized equipment because it allows for much faster setup than permanent, stick-built plants. But even with modular kits, the commissioning process is rigorous. You're testing safety shutoffs, checking the fuel-to-air ratios in the engines, and ensuring the synchronization with the facility's electrical bus. You need experienced field crews who live and breathe this stuff. It's not a set it and forget it situation.
That leads perfectly into the ongoing operations. Once the first megawatt is flowing, the real work of reliability begins. How do you monitor a system like this to ensure it doesn't just work on day 1, but on day 1,000?
Continuous monitoring is the only way. We're tracking everything in real time: fuel levels in the tanks, engine temperatures, vibration levels, and electrical output. We use remote telemetry so that if an engine has a minor sensor glitch, our technicians might know about it before the on-site team does. This also ties back to the fuel logistics. The monitoring system predicts when the next LNG delivery is needed based on actual consumption rates. If the data center suddenly starts a massive AI training run and fuel use spikes, the logistics team sees that instantly and adjusts the truck schedule. It's a feedback loop between the power demand and the fuel supply.
What about when things go wrong? We're talking about mission-critical sites. If a truck gets stuck in a snowstorm or an engine part fails, how do you prevent a total blackout? The contingency planning side must be robust.
Contingency is where the fulfillment part of the name really proves its value. It's why we maintain redundant fuel storage on site. Most sites have several days of fuel buffer to weather transportation delays. We also keep critical spare parts nearby or even on site and have rapid response field teams. But it's also about the system architecture. By having multiple generators instead of one giant one, you've built in mechanical redundancy. And because UNRG owns the full chain, there's no finger pointing between a fuel guy and a generator guy. There is one point of accountability to keep the lights on.
I want to touch on scaling. Many of these projects, especially data centers, don't stay the same size for long. They're constantly adding capacity. How does a distributed energy system grow with that demand?
That's the beauty of the modular approach. In the old world, if you needed more power, you'd have to beg the utility for a new substation, which could take years. With the energy fulfillment model, scaling is almost like adding Lego bricks. If the load increases by 5 megawatts, we can deploy another 5 megawatt block of generation and add more LNG storage capacity to match. We can do that in weeks, not years. This allows companies to tie their capital expenditure directly to their actual revenue growth. They don't have to build a 100 megawatt plant on day one if they only need 20.
When we look at the sectors doing this, aerospace, aggregates, remote mining, and obviously data centers, the common thread is that they cannot wait. They have a business opportunity today that the current grid infrastructure simply cannot meet. But as we've discussed, jumping into distributed power isn't as simple as buying a generator.
It's a complete shift in how you think about energy. You're moving from being a passive consumer of a utility to being the operator of your own energy supply chain. That's why the integrated platform is so vital. Most of these companies, whether they're building rockets or running server farms, don't want to be in the power business. They want the outcome. They want the megawatt. By coordinating the fuel sourcing, the cryogenic transport, the regasification, and the generation through one platform like UNRG, they get that outcome without having to manage 5 different subcontractors who don't talk to each other.
It really highlights that reliability isn't a product you buy. It's a process you maintain. You can have the best engine in the world, but if the truck carrying the fuel is stuck at a terminal because of a paperwork error, you have a 0 megawatt system. The integration of the physical molecules and the electrical megawatts is the real innovation here.
Exactly. Reliable on-site power is an ecosystem. It requires the logistics of the molecules in motion fleet, the technical precision of modular regasification, the flexibility of be the grid generation, and the constant vigilance of field operations. When those are all aligned, you aren't just surviving a grid constraint, you're operating with a level of independence and speed that the traditional grid just can't match.
Moving from fuel source to the first megawatt is a complex journey, but it's one that is becoming mandatory for industries that need to scale now. It's clear that the path to energy security isn't found in a single piece of equipment, but in the coordination of the entire fulfillment chain, from the ground to the generator. Share this episode with someone navigating the complexities of industrial energy and the move toward distributed power.